So hello everyone. Today we are going to discuss the complete chemical property of metals and its compounds. Okay. So chemical properties of metals and its compounds. First of all, let us know a little bit about the chemical properties. So the chemical properties are the properties which leads to the chemical change, and this chemical change may be their color changing, maybe their appearance changing, maybe we are having gases, temperature changes, we are getting some of different smells. So these are the characteristics of chemical changes. Then let's go to the topic. Topic is that chemical properties of metals and non-metals and its compound. Okay. So metal means what? Let's try to know. Metals. So metals are the element. Metals are the element which always wants to donate electron. Wants to donate electron. So obviously we can say if it is a metal, okay, metal solid, it produces Mn positive plus N electron, it is equals. Okay, that means the metal will donate or loses some number of electrons. Okay, metal loses electron. If any species loses electron, it becomes electropositive, and the species which accept electron is known as electronegative. So that's why matter should act as an electropositive. Okay, but the number of electron which is leaving, that means removing or gaining, it will depend on the particular metal. For example, if you take example of sodium, then sodium will remove only one electron and become only one positive, because this number of one electron will be based on their valence shell electronic configuration. Okay. Similarly, if we see potassium, then also it become K plus one electron removes. But if you see magnesium, which removes 2 electron. See, in sodium, potassium 1, but magnesium is 2, and this number, that means 1 or 2 or 3 or whatever the number it is, it will exactly depend on their valence shell electronic configurations. Let's see a little bit how it is. For sodium, we know the valence shell electronic configuration is 281. So this 1 electron in the valence shell, if it is removes, it gains the 2,8 stability is given by the octet rule. Okay. So similarly, if you see magnesium, so it is 282. So if it removes 2 electron from its valence shell, it will gain the 2,8 configuration stability, again explained by the octet rule. So here, up to this much we know about the metal and its nature. Okay. So now, what about the metals we have in our modern periodic table? Remember, in modern periodic table, left elements are all the metals, okay, and the right side elements are non-metal. Okay, but in middle of left and right we have some metalloid also. Metalloid are the element which can act as a metal, as a non-metal, both. Okay, but it will depend on the conditions, depend on our criteria. Simply you cannot say. Okay, it will depend on the conditions, at which conditions you are reacting that element. Then if it is acting as a metal, then metal. If it is acting as a non-metal, then non-metal. Okay. For example, the well-known metalloid are suppose gallium. This is a gallium. Okay. So now let's see about the metals. We are not going to the metalloid. Okay. So let's see the metals. So see, we have more number of metals, but if we have more than 2, more than 5, 10 number of elements or metals, no, then you should know which one will act as a better metal, or which one have the better metallic character, which one has a less metallic character. To know about their reactivity, their metallic behavior, their little bit chemical nature, we have to know the activity series of metal. This is known as the reactivity series of metal, and the series that I am going to write, that series will say which one will be least reactive, that means does not want to react, and which one will be most reactive, that means which is very frequently, very easily wants to react. Okay, so let's see the activity series. Now see, in this activity series of matter. Okay, so from here to here, it is the activity, or you can say reactivity, decreases. So that's why it will be the most reactive. I am writing in the red pen. Okay, so these are sodium, potassium, barium, calcium, magnesium. These are most reactive. But suppose these are those mercury, silver, gold, platinum. These are least reactive. These are least reactive. So now you can say, or with this simply you can say that these are the metals up to this much is a better reactive, or that means it wants to react. But these are the some metal which do not want to react. Okay. And the middle of this element are in medium reactive, sometimes reactive, sometimes not. Okay. Now remember one thing, here we have an element, it is the hydrogen. But hydrogen is not a perfect metal, at the same time it is not a perfect non-metal, as hydrogen has the resemble or similar character to the metal also, to the non-metal also. Okay, we are keeping in this place. We are keeping hydrogen in this place in their metallic behavior. Here we are not discussing its non-metallic behavior. Okay, so don't confuse. And if you say, sir, why we have taken hydrogen if it is having non-metallic character also? Here only we are taking metallic behavior. That's why we are keeping this. Because hydrogen has a very good tendency to produce H plus and removing one electron. That's why if a species can remove electron easily, it should be act as a metal. That's why it has a metallic character, and we are keeping in this position. Okay. So this is the activity series. Now let's go to the chemical reaction of this metal with the oxygen. Okay, with the oxygen. So let's see. So let's see. So it is reaction of metal with oxygen, O2. Okay. So most of the reactive metal have the affinity towards the oxygen. Affinity means they want to react with the oxygen, but their, you can say, reactive nature may be less, maybe more. It is a different thing, but has the ability to react, except some element or metal which are listed in the least reactive position. Suppose it is mercury, gold, platinum, these are. Okay. But the metal is given, no, that sodium, potassium, aluminum, zinc, copper. This has the ability, not sorry copper. Other copper has the ability or capacity to react with the oxygen very easily. Okay. For example, generalized reaction I am writing, any metal if react with metal react with oxygen, it produce metal oxide. For example, if I am taking sodium plus O2, it produce sodium Na2O. Similarly, if I take magnesium plus O2, it produce MgO. Now remember one thing, it's a very serious thing you got in class 9. Okay, that one oxygen can combine with two sodium, one oxygen can combine with one magnesium. These are completely depend on their valency. And valency is the simple combination power, combining power of respective element. Okay. Thus sodium has the valency equal to 1. Okay, oxygen has valency 2. That's why 2 will be taken by sodium and 1 will be taken by oxygen. That's why it becomes Na2O. Okay, this is the thing. It will be, I'm just reminding you. Okay. Similarly, if you see iron is a bit in different nature. Iron Fe plus O2. Okay, so iron, if you take, it is suppose iron if you take 3, 2, so Fe3O4. This Fe3O4, it will be having exceptional behavior, unique behavior. Okay, and the behavior is here. One is FeO, another is Fe2O3. Okay, so here Fe2. Here the iron is +2 state, it is -2, so it is neutralizing. Here iron is +3. Okay, oxygen is -2. 3 into 2 6 plus 6, 3 into 2 6, it is -6, so it is balancing. That's why in the single compound only we are getting two oxidation state of iron. One is +2, another is +3. Okay, clear now? So in Fe3O4 we are getting two types of oxidation state of iron, +2 as well as +3. Okay, so next. Next, continue this topic only. Okay. Next, we have some oxide, or you can say some metals. Metals are copper, aluminum. These are the metals which are not that much reactive that we are thinking. Copper can form copper oxide, aluminum can form Al2O3, aluminum oxide. But remember one thing, always I said no, that manner of combining the oxygen with copper, oxygen with element, it may be copper, it may be element, will vary, and it will depend on the individual element. Suppose copper here having valency or oxidation state, it is +2, it is -2, and one aluminum is +3, one oxygen is -3. As we are having 2 aluminum, so it becomes +6, 3 plus 3 6. Here it is 3 oxygen, so 3 to the 6, -6, +6 -6, +6 for the 2 aluminum, -6 for the 3 oxygen. That's why they are combining and forming electrical neutral compound. Okay, this is a very silly thing, but you have to be very clear with that. Okay, so that's why. So I'm not going that one. Okay. But main thing, these two elements or like that metals, okay, have a medium tendency to react with the oxygen. It's not that much high that we are thinking. Okay, this is the main reason for suppose aluminum or copper, they are used. Aluminum or copper are used to make utensil. Maybe karai. Okay, I don't know the proper spelling of karai. Okay, karai, karai, whatever you say. Okay, it may be any suppose utensils to make to prepare or to cook our food. Okay, so question may come from here. Question may come, as we know that aluminum and copper are active metal, though why we are using to make our utensil? The answer is though aluminum and copper, suppose aluminum is the reactive metal, okay, whenever it react with the oxygen, it produces aluminum oxide, which is inert in nature and it is not reactive with our food. So we can prepare our utensils with the help of aluminum metal. Because again, so suppose it is a utensil metal, no? Suppose it is a karai. Okay, so if it is made up of aluminum, then this aluminum will combine with water and form a layer of aluminum oxide on the utensils, which prevent from the harmful chemical reactions between this element and our food. Okay, so next, how this metal, now these are metal oxide, no? Now we will see how this metal oxide react with water. How this metal oxide react with water. So let's see. So you can write here reaction of metal oxide with water. Remember, whenever it produce, okay, whenever it produce metal oxide reacting with water, it produce metal hydroxide. Metal hydroxide. For example, I am the example of sodium O sodium oxide plus water, it produce sodium hydroxide. Similarly, if you take suppose MgO plus water, it produce MgO. It is 2 magnesium, it is 2 OH. Okay, 2 OH. Similarly, sorry, here it will be 2. Okay, because the valency of my magnesium is 2. Now look that this is a pure hydroxide A base. This is a pure hydroxide A base. So now we can say that the metal oxide are having basic nature upon reaction with water. Okay, so nothing but simply we can say this metal oxide are also basic in nature. Metal oxide are basic in nature. Finish. So their pH will come, okay, more than 7. More than 7. Actually, for sodium hydroxide, the pH is coming at nearly 13, 14. That much basic. Okay. But we have some oxide. We have some oxide which can react with acid as well as base, and these oxide are known as amphoteric oxide. For example, one amphoteric oxide is aluminum oxide and zinc oxide. Will come later portions. Okay, later portion will come. Okay. Now next is that the reaction of metal oxide with the acid. Reaction of metal oxide with acid. How acid will react with the metal oxide? Obviously, whenever metal oxide, suppose it is a calcium oxide, react with HCl, acid. This is a base, this is a acid. It will react with to form salt. And for this example, the salt is calcium chloride plus water. Obviously, it will form. So salt plus water. Finish. So now, as we have seen now, that metal oxide are amphoteric in nature. So let's see one example of amphoteric nature of metal oxide. So one I'll do, one you just go through this. Okay. So first one is aluminum oxide. Al2O3 can react with HCl. Al2O3 can react with sodium hydroxide also. Okay. When react with hydrochloric acid, it produce okay, it is 6. So AlCl3, it is 6 plus 3 water. When it react with sodium hydroxide, that means base, it react like that, 2 sodium AlO3. Okay, O2, sodium aluminate, O2 plus water, So now if you notice, then you will get that here it is acting as a basic weight. Here it is acting as a basic, it is already acid, so it is giving salt plus water. But here this is a base, so it is acting as a acid and giving salt and water. So now we can say that same aluminum oxide, depending on their conditions or reason, acting as a basic, sometimes acting as a acid, basic and acid. That's why these are amphoteric in nature. I think it is clear. Okay. So next, see. Okay. Now this is the finished the metal oxide. Okay. Now let's go to the again reaction of metal with the hydrogen. Reaction of metal with hydrogen. Metal react with hydrogen to form hydride. Metal react with hydrogen to form metal hydride. For example, sodium react with hydrogen, it produce sodium hydride. Suppose calcium react with hydrogen, it produce calcium hydride. Like this, hydride. Okay. Now here, this calcium hydride, again, if it is react with water, it produce sodium hydroxide plus hydrogen gas. It is react with, if it is reacting with water, it will produce calcium hydroxide plus hydrogen gas. This way it will produce. Nothing but what? This hydride also, it is basic in nature. See, it is forming basic. So basic in nature. Now here is the very important term that we have to remember is that this calcium hydride, calcium CaH2, calcium hydride is acting as a drying, okay, Dr. Calcium hydride acting for drying agent. That means act like a drying agent. We can dry the substance with the help of calcium hydrides. And it has a unique name, and this unique name is known as hydrolith. Okay, hydrolith. Hydrolith is the common name of calcium hydride. Okay. So next is the reaction of metal with the water or air. Okay, directly. So metal reacting with water, it produces metal hydroxide. Suppose sodium plus water, it produces sodium hydroxide plus H2. Now see, some metals are very explosively react with water. For example, one is sodium, potassium, these are very explosively react. And this is how it is explosive. I will show you in the laboratory. Okay, so we will get how it is explosive. Okay. It may catch fire also in the water only. It may catch fire also. But the rest of the elements are not that much reactive with the water. Yes, reactive, but not that much reactive like sodium or potassium. Okay. So as it is very explosive. Okay, explosive with respect to water. That's why we cannot keep our sodium and potassium in the open space or water. Open space also have huge amount of moisture. So that's why we have to keep our potassium, sodium in the medium absence of water. And the medium is normally we are taking is kerosene. We can keep it in petrol, diesel also, but we normally are keeping it kerosene, which is water free. Okay. So next. Okay. See, up to this much now, this material highly reacting. Here we will get a huge amount of heat also. Explosive, no? Heat. But that's why we can say this is an exothermic, because it produces heat. Exothermic. But some metals are reacting with oxygen or water, which are endothermic in nature. Endothermic means we have to supply heat from the external source. Okay, external source. Okay. For example, if I am taking magnesium plus water, we have to give some amount of heat. Not that much, little bit heat. 50 degree, 40 degree centigrade. Okay. The magnesium will react MgOH. It is 2 plus water. It is 2. Okay, magnesium hydroxide. This is also base, but this is needed temperature to produce the chemical or product. That's why it is a endothermic. And this is not that much explosive. It's not an explosive reaction. It's normal reaction. Okay, but some metals are there. Suppose it is gold, mercury, okay, silver, platinum. These are the metals which are inert in nature. Inert means they does not want to react. Okay, so for that we have to so for this one, oxygen or water, with respect to water, oxygen, these are inert in nature. That's why now if you notice gold, maybe silver, maybe platinum, we are using to make our jewelry. Okay, to make jewelry, because it is not reacting with the with the body part. Suppose here I am wearing jewelry, here I am wearing jewelry. Suppose in neck also lots of jewelry. Maybe especially the girls, they are wearing lots of jewelry. So if they were react with the skin, no, so they can have what function of metal with the acid. Okay, as you know, acids are very corrosive and reactive in nature. So the acid can react with our metal also to form different product. So that's why if I am taking a metal, suppose the metal is sodium, which is very reactive. Okay, which is very reactive. So this metal, if it is reacting with our ACl, it can produce ACl. Okay, sodium chloride, not ACl, sodium chloride and the hydrogen gas. See, so it is what? Metal, acid, salt, hydrogen. Okay. Similarly, if you take another one, suppose I am taking magnesium plus H2SO4. Magnesium also metal. Sulfuric acid is very strong acid. So if I am taking like that way, then it can have magnesium sulfate plus hydrogen. This is also a salt. This is the hydrogen gas. Okay, salt plus hydrogen gas. Okay. So now, whatever the hydrogen gas here is produced, we can detect by the passing of this hydrogen gas with the soap solutions and the burning of the gas. It will give the pop sound, as I have said in the chapter 1. Now, if we see the copper is a metal. Copper is a metal. So copper react with, suppose if we are giving HNO3, it should be react like that, salt, because metal and strong acid. Okay. But actually we are not getting that type of chemical reaction here, because it is not producing any kind of salt and hydrogen. The reason is that this is a very good oxidizing agent, very good oxidizing agent, and it oxidizes this HNO3 and the copper also to form the hydrogen gas. Okay, so to form the water, not hydrogen gas, to form the water. That's why we are not getting any kind of hydrogen gas or this type of reactions. We are getting water only, water and rest of the chemicals. Okay, so similarly, if we see zinc, for the zinc I am writing. Okay, try to write the ratio between the copper and nitric acid. Okay, so I am giving the ratio between the zinc and nitric acid. So zinc also when zinc react with HNO3. Okay. Zinc is also metal, nitric acid is also an acid. So it should be react to form the suppose you can say salt and hydrogen gas, which is usual. But in this type of category, suppose zinc reacting with nitric acid and copper reacting with nitric acid, the general rule, that means salt plus hydrogen gas is not forming. It is forming like that. It is zinc. Okay. Zinc NO2. Okay, this 2. Zinc nitrite. Okay, or you can say zinc nitrate also you take. So here it is, if you take then it is 4. So zinc nitrate is forming, and then it is forming 2 NO2 gas, and it is forming some amount of water. Okay, water is, if you take it will be 2 and it is liquid. Now just try to match or try to balance if the ratio is balanced or not. Let's see. Zinc is how much? 1 zinc. Hydrogen is how much? Hydrogen is here 4 hydrogen. Okay. So here how much hydrogen? 2 to the 4. 4 hydrogen. Correct. Nitrogen here is 4 nitrogen. 2 nitrogen. 4 nitrogen. It is 4. Oxygen here 4 3 is 12 oxygen. Now here see 3 to the 6 oxygen. 2 to the 4 oxygen, and here it is how many oxygen? 2 oxygen. So it is 12 oxygen. So the reaction is balanced, and the reaction does not have any kind of hydrogen gas, because this nitric acid oxidizes to form our water, water. Okay, so question may come, the exceptional behavior of copper and zinc with respect to nitric acid, like that. Okay. And the last topic for today's class or video, it is the aqua regia. Aqua-regia. Okay. So aqua regia is one of the most, you can say, very strong acid which is formed by the mixing of hydrochloric acid and nitric acid in 3:1 ratio. So aqua regia. Okay, aqua regia. Aqua regia, and is the mixture of hydrochloric acid and nitric acid. Okay, hydrochloric acid is to nitric acid ratio is 3:1 ratio. 3:1 ratio. That means 3 part is hydrochloric acid, 1 part is nitric acid. Okay. So this acid is known as the royal water. This acid is known as royal water. Okay, royal water, and it is using in the cleaning of especially jewelry. Cleaning of jewelry. That's why if in the jewelry shop, goldsmith, they are using that acid to clean our jewelry. After cleaning, it become very shiny, very glazy. Okay. So this is how they react. What is the chemical reaction behind that cleaning? Say suppose I am taking the gold reacting with chlorine. One second. Wait. Whenever it produces, suppose I am adding HCl plus HNO3. When hydrochloric acid reacting with nitric acid in the manner of 3:1 ratio, then we will get NOCl, nitrosyl chloride, and then nitrosyl chloride plus water plus Cl2. Okay, plus it is 2. Okay, it is 2 plus Cl. This Cl is alone Cl, not Cl2. Remember, this Cl is Cl, not Cl2. And this type of single Cl is known as nascent chlorine or nascent Cl. And this nascent chlorine is very reactive in nature. So that's why whenever this is used to cleaning our gold jewelry, this nascent chlorine, here is a gold jewelry, Au gold, this gold jewelry will come to react and is formed AuCl2. This AuCl2 initially it has very shiny character, but after some time, 5 or 10 years after using, it become little bit fad. That's why whenever we are purchasing a new gold jewelry, it become very shiny. After some years, the shiny character may little bit fade. But again, whenever we clean it, again it forms AuCl2, and it gives the shiny or glazy appearance. Okay. So this much only from today's class. Okay. So let's see in the next class. Okay. So thank you. Have a good day.